Your WebRTC demo application works perfectly on your own Wi-Fi network. But the moment a real user joins your call, it dies. This is exactly how most WebRTC demos break. They only work on the same Wi-Fi, but real users join from 4G, hotel Wi-Fi, or locked down office networks. The signaling still looks fine because Firebase is just passing offers, answers, and ICE candidates. But the actual media path is blocked by street NATs, firewalls, or missing turn server on TCP. So ICE quietly fails and the call never stabilizes. In this Android-focused course, we will start from a simple Firebase demo and turn it into a production-ready WebRTC stack. Correct stun and turn server configurations, handling symmetric NATs, robust signaling and reconnections, foreground service for background safety, and a lot of useful things that we'll do in this course. So make sure you don't miss this tutorial. Alright, before we touch a single line of code, let's actually talk about why this storage stuff matters. If you have ever tried a WebRTC demo that worked perfectly on your home Wi-Fi and then completely died in the real world, that's exactly why this episode exists. On the surface, WebRTC feels really simple. Create a RTCP connection, send an offer, get an answer, and then add some ICE candidate, boom. You have the video call. But in production, users are in 4G, behind dirty NATs, corporate firewalls, or VPNs, or 10 different Android devices that love to kill background process. If we don't deeply understand what's happening under the hood, every bug will look random, and every failure will feel like WebRTC is just flaky. What we're going to do in this episode is going to build a mental model that make all of that predictable. So when you understand how signaling is totally separate from media, how ICE really searches for path, when stun server is enough or when turn service is absolutely mandatory, and why NATs and firewalls behave like angry gatekeepers, then suddenly the code in production-ready WebRTC that we are covering right here stops being magic and starts being obvious. You will know why there is a turn config, why we care about ICE states, why we need a foreground service, and why mesh versus SFU versus MCU is not just an architecture choice, but a cost and reliability decision. Think of this section as reading the map before your trip. Yes, you can dive into the code before watching this episode, but you will for sure get lost. So in the next few minutes, we are going to stay away from Android Studio and instead zoom out. We will look at the full WebRTC architecture. We will see where signaling, stun, turn, and media actually flow. And we will connect all of that directly to the source that we are talking about. Once the model is clear, when we finally open the code, you will see the production-ready WebRTC is not just a sample. It's a direct implementation of everything that we are talking about. Alright, with that in mind, let's start with the big picture, how a perfect WebRTC call flows when everything actually works. Look at this diagram as the Google Maps of a WebRTC call. On the left and right, we have two user devices. In the middle, we have three different backend roles: the signaling server, the stun server, and the turn server. The blue path that hits the signaling server is only for setup messages, offer, answer, and ICE candidates. No audio or video goes through it. The green solid line is the ideal case, a direct peer-to-peer media path between two devices. When that fails, because of NAT or firewalls, the orange dashed line shows the fallback. Media relied through the turn server. When you are debugging a call, you should always ask, are my signaling message flowing? Did stun give me public candidates? And did ICE manage to choose either the green direct path or the orange turn path? This diagram is here to separate two ideas that developers often mix up. The top line is signaling your own code, often WebSocket or Firebase, which just pushes JSON messages like SCP and ICE between clients. The bottom line is media, the WebRTC engine sending encrypted RTP or RTCP packets directly between peers or through turn. If signaling dies after the calls start, the current media may continue for a while, but you lose the ability to renegotiate or restart ICE. If the media path is black but the signaling is fine, you will see all the right events, but the remote video stays black. So in production, you must monitor both signaling health and ICE media health. Here you can see how ICE does its job under the hood. Each client collects three kinds of candidates: host candidates from local interfaces, server reflexive candidates from stun, and relay candidates from turn. The diagram shows ICE building a list, then sending those ICE candidates to other sites through signaling. Both peers then start connectivity checks. Small stun binding requests sent between every possible pair of candidates. The first pair that responds and meets your policy becomes the selected path. If you only ever see host candidates and no SRFLX or relay, that's a red flag. Your stun or tend configuration is wrong. If IC ends in failed, it means none of these candidate pairs worked. This visual shows the conference room demo with the messy real world. On the left, both devices sit on the same friendly Wi-Fi. Open NAT, no firewalls, stable connection. But in the vault, almost any WebRTC sample app looks perfect. On the right, we have a realistic situation. Different networks, mobile data, corporate firewall, maybe a VPN, maybe packet loss. Here, stun may fail to punch through. Turn may be required just to get a path at all. Android may move the app to the background or kill it. This figure is a reminder. If your app only works in the left diagram, it is still a demo, not production ready. Now let's take a look at group call topologies. When more than 2 people join a call, you need to choose a topology. There are 3 main options: mesh, SFU, and MCU. Choosing the wrong one can make your app slow, expensive, or impossible to scale. Option number 1 is mesh, or pure peer-to-peer connection that you can see in this diagram. So in this architecture, every participant connects directly to every other participant. No server needed, but each device uploads n-1 stream at the same time. So problem here are a very high CPU, battery, or data usage, and phone of course gets overheats and unstable with +4 people on mobile. Option number 2, SFU, or selective forwarding unit. In this architecture, each device sends one stream to the SFU server. SFU routes it to other participants without mixing or decoding, the modern standard for group calls. So each device uploads only one stream, no matter how many people join. Server just routes, no decoding, server cost is low, supports adaptive quality per participant, scales to +50 participants, end-to-end encrypted is possible. So it's best for meeting, classrooms, and most Android conference apps. Option number 3, MCU architecture, or multi-point control unit. The MCU decodes all streams, mix them into one combined video, and send that track to everyone. Very simple for the client, but very expensive on the server side. So each device downloads only one stream, the pre-mixed video, good for recording, only one clean file, works for large webinars with one presenter, very high server CPU cost, of course, and it's too much expensive to scale. No end-to-end encryption is possible. Fixed layout, participants cannot change their view. Of course, it's best for large webinars, legacy enterprise systems, server-side recording. So in case of choosing which architecture fits your profile, let's say if you have 2 people only, you go with the mesh. No server, lowest cost. If you have between 3 or 12 people in a meeting, you definitely want to go with SFU architecture. And if you have +50 viewers or needed one recorded video, you want to use MCU with recording. And if you have Android mobile users in a group call, remember, always prefer SFU over mesh. And now it's finally time to deep dive into the NAT types, dirty NAT, and firewalls. NAT stands for Network Address Translation, is one of the main reasons that WebRTC calls fail in the real world. Not all NATs are the same. Some NATs are open and easy to work with, others are very strict and blocked almost everything. So if you want a bit more details about NAT or Network Address Translation, it's how your router lets multiple devices share one public IP address. Your home device uses a private IP, let's say like 192.168.110, and another one uses 192.168.111, and your ISP gives you one public IP, let's say 203.0.103 and 5, then NAT translates between them. So look at the diagram. You can see multiple devices inside connection to the internet through a single IP address. So how it works? Your phone sends a request to a server. Let's say it has an IP with 192.168.110 and sends a request to the server. So what router does, it replaces the private IP with your public IP, which was 203.0.113 and 5. Then router remembers this mapping in a NAT table. When the server responds to the public IP, router forwards it back to your phone. This is called PAT, or Port Address Translation, which most home routers use this. So why NAT matters for WebRTC? The problem with NAT is that NAT blocks incoming connections by default. For WebRTC peer-to-peer connection, outgoing connection works fine, your device initiates. Or when it's about incoming connection, router doesn't know where to forward. So to fix this issue, you have to use stun server that tells your device its public IP. That tells your device its public IP or port, for NAT traversal of course. And in case of restrict or symmetric NATs, we have to use turn server, which acts as a relay when direct connection fails. Understanding the 4 NAT types tells you when turn is required and when stun is enough. So in this diagram, you can see 4 NAT types. Option number 1, full cone NAT or open NAT. Once your device sends a packet out, the router creates a public port mapping. Any external host can send packets back to the mapping, even if you never contact them before. So this NAT type is most permissive NAT type. Stun works perfectly. Direct P2P connection almost always succeeds. And it's of course common on some home routers and open networks. Option number 2, address restricted cone NAT. This NAT type has same port mapping as full cone, but only hosts that your device has already sent a packet to can send packets back. Unknown outside hosts are blocked. So stun still works. ICE can coordinate both sides to send first. P2P usually works with a simple hole punching technique and is common on some routers. Option number 3, port restricted cone NAT. It is like address restricted, but the restriction also includes the port numbers. The external host must match both the IP address and the port that your device originally sent a packet to. So stun still works in many cases. P2P works if the other peer is not behind symmetric NAT. Very common, most home routers use this type, and of course it fails when paired with a symmetric NAT on the other side. And the last type, or symmetric NAT, it's called strict NAT or dirty NAT. This is the most restrictive type. Every time your device connects to a different destination, the router assigns a different external points. So the port that the stun server sees is not the same port that remote peers would see. So the port that the stun server sees is not the same port that the remote peer would use. So in this type, stun cannot connect. It sees one port, but the real peer gets a different one. Of course, standard UDP hole punching does not work. Very common on carrier, grade NAT or mobile network. corporate network and VPNs. And mobile data, 4G or 5G, almost always uses symmetric NAT. So in the context of WebRTC results, turn is always required. When one or both peer are behind symmetric NAT, this is why turn is mandatory in any real production app targeting mobile users. You can use this matrix to understand which NAT combination requires turn. The rows are peer A's NAT type and columns are peer B's NAT type. The key rule here is if either peer is behind symmetric NAT and the other peer is behind port restricted or symmetric NAT, turn is always required. Since most mobile devices, Android users on 4G or 5G are behind carrier-grade symmetric NAT, you must always have a working turn server in any production app. Now let's take a look at firewalls and port blocking. On top of NAT, corporate network and strict environments add firewall rules to block WebRTC traffic even further. This is something called a dirty network, a network that blocks almost all non-HTTP traffics. Many enterprise firewalls block all UDP traffics. Only TCP/AT and 443 are open. Standard stun on UDP port 3478 is often blocked by Palo Alto and other enterprise firewalls. So what's the solution here? You have to run your 10 server on TCP port 443 with the TLS. To the firewall, this traffic looks like normal HTTPS and passes through almost any network. Some deep packet inspections or DPI system can detect and block stun even on port 443. In these extreme cases, a custom turn configuration on a trusted domain is needed. Always test your turn server from inside a corporate network or on mobile data before claiming your app in production ready. So in most of the cases, if you deploy a turn server on TCP port 443 with TLS in additional to UDP 3478, this ensures your app works on mobile data or symmetric NAT and in corporate office or when UDP is blocked. Alright, let's wrap up this episode. You have just seen why most WebRTC demos look perfect on a conference room, Wi-Fi, and then completely fall apart in real world. We walked through the happy path, then broke it on purpose with NAT, firewalls, broken turn servers, buggy signaling, Android background issues, and bad group call architecture choice. Now, when a call states stacked on connecting or ICE flips to failed, it should no longer feel like random WebRTC magic. You know which part of the system to suspect first. You also saw big topology choices. Mesh versus SFU versus MCU, when stun is enough and when turn is not negotiable, and how strict NATs and corporate networks basically force you to design for the worst case, not the ideal demo network. If any part of this video still feels fuzzy, maybe NAT types, ICE behavior, or topologies, that's totally fine. Pick one area that you want to be rock solid on and tell me which one is it, so we can reinforce it before we move to the code. Thanks for watching. Till the next video, see you everyone.